At a recent channel meetup on the Isle of Man, I was given a couple of ultrasonic pest repeller devices that are apparently faulty. They used to light up, they don't light up anymore. Having plugged them in, I can hear the click of the ultrasonics. Obviously, ultrasonic you can't hear. Let me just zoom down this. That's a good start. Obviously, you can't hear ultrasonic sound because it's beyond human hearing, but you can hear a click from this, which does suggest a sort of sweeping frequency perhaps. So these two units appear to be identical except for the logo on them. If I plug one of these in and let you hear it, I don't know if you'll hear it now. Hopefully it won't swamp the microphone out in the device. I'm not sure how sensitive it is to ultrasound. Well, let's find out. I shall plug it in and I shall hold it up to the microphone of the phone. Now, if you're hearing what I'm hearing, I'm not sure what will actually come through that, it's a clicking noise. So that does suggest that they're active. Let's open it up and see what circuitry is inside. It's not going to fit. What have I got? This one? That'll do. Bright white, not great for filming. It just tends to swamp out a little bit. It's a tricky balance for exposure. Is it clipped? Oh, it's not too badly clipped. So there is an ultrasonic disc. There's the chip. There's what looks like a capacitive dropper capacitor. Right, tell you what, I'm going to take a picture of this circuit board so we can get a much closer look and we'll reverse engineer it. One moment, please. Here we have the circuit board. So what I'm seeing here, let's just zoom down a little tiny bit. I will do some tests as well. So we get live and neutral coming in, and we've got another side of the circuit board. Actually, I'll whip the cover. No, I won't whip the cover off. I'm about to plug this in. That's a bit shitty. But there is a capacitor on the other side, and then there's a couple of discharge resistors across it. And there's a 100 ohm resistor tucked in under here, which goes from the neutral to the other end of the bridge rectifier. And that means it's basically a capacitive dropper. On the output, there's a Zener diode, and then a smoothing capacitor, and then a sort of decoupling capacitor over here, just to actually protect the microcontroller from little transient glitches. Different countries have different names for this capacitor. It seems to be a controversial thing. However, let's plug this in. And to do that relatively safely, let's bring the meter in. I want to measure the voltage on that. I'm going to guess that it's going to be 5 volts because it's going straight to the microcontroller. And that would make sense. So I shall plug this in to the happy, and it's not going to register anything. I tried. And I'll just zoom out for this a little bit. I shall plug it in. And then I shall probe directly across the electrolytic in there, noting this whole thing is live, including the piezoelectric sounder in there. So this should be the positive, and this should be the negative. We have just over 5 volts. Okay, so I'm guessing this might actually be a 5.1 volt Zener diode, which is a very standard value. And there'll be a bit of ripple, which would make that look a bit lower again. Right, now I can take it out. I can unplug this. I'll give it time to discharge. Has it discharged yet? Yes, it has. So a couple of screws holding the circuit board in. And that will reveal the capacitor on the back and the resistor and the electrolytic capacitor. So here we have, let's zoom down, the dropper capacitor, which is a value of 560 nano, 400 volt. It's got the 100 ohm resistor, brown, black, brown, 1 0 and 1 as an additional 0. And then we've got the electrolytic capacitor, which is 220 microfarad at 16 volts. It's only being used at about 5 volts, but 16 volts is a sort of minimum value. It's a generic value for these. Let's zoom back out and explore the circuitry. So we have the capacitive dropper, we have a microcontroller here, and it's only using 2 pins. What is under that black thing? I'm pretty sure it's an LED. It is an LED. It's a little white LED by the look of it. I bet that's failed. Where's the meter? Let's stick the meter across it. That should give an indication if it's still working or not. Usually you can make the LED light. So the positive end will be here, and the negative end will be there. It's showing an unusually low voltage across it, and it's not lighting. That means it's a dead white LED. How very typical of shitty white LEDs. Excellent. So that's an LED under there. I'll just draw that in on top. There's an LED under here. The piezoelectric sounder, speaker 1, speaker minus, speaker plus, is driven by this transistor, which is a standard NPN transistor. Oh, what the heck, let's cut straight to the schematic. And I'm going to break with tradition here. I'm going to actually draw. Well, it's going back to the beginning of this channel, when I just reversed engineered things on the fly. This is looking a bit ferocious, that's all right. Oh, I'll use my special pen that's stuck to the notepad, that's an idea. So we got the incoming supply, live and neutral. There's a sine wave showing that it's the mains. And the first thing it hits is this dropper capacitor with the resistors across it. So it comes in, and there's a dropper capacitor, and across that are two resistors. The resistors are 470k each. This actually hints at goodish design, actually. So 470k times 2 gives roughly, say, close to 1 mega ohm, but close enough. 560 nanofarad, 400 volt classic capacitor. On the neutral, we're going via this resistor here. This little metal film resistor here, which doubles up as both inrush surge limiter and also a fuse when things go horribly wrong. Although, having said that, I looked this up online to see if I could find if they were still about. And someone had a picture of one on Amazon, which was clearly exploded. And it was very sooty. It hadn't survived very well at all. The whole lot had just basically splattered everywhere. Nice. I come to think of it, that disc dropped out on it. It's possible the disc had dropped out and shorted out the... Yeah, that would have been exciting. That would have worked. That would have done it. So here's my lazy rectifier. Here's positive. Here's negative. Here's the 100 ohm resistor. The output, then, is the positive rail and the negative rail, which we shall refer to as 5 volts, because it is clamped down to that, and 0 volts. The 0 volt is the circuit reference. It's not 0 volts with respect to Earth, because it's actually directly referenced to the mains here. And on output, the first thing it actually hits is this Zener diode. So let's draw a Zener or Zener diode in, depending on how you like to pronounce it. Apparently, the person who invented it, his family referred to him as Zener. But it's a controversial area again. The world is full of controversy. Then there's a smoothing capacitor, a little electrolytic, which is rated 220 microfarad, 220 microfarad at 16 volts. We'll say this is just 5 volts, this is Zener diode. Then there's a little decoupling capacitor. I'll just squeeze it in here. And if I probe through on this circuit board from this side to this side, these power rails run straight underneath. So there's actually a 1k resistor across that as well. This is probably to ensure a good solid reset when the power's turned off, but I would say that 1k is actually quite low. I think 10k would have been better for that, particularly given it's based on a capacitive dropper. But after that, it goes to the microcontroller. Doesn't everything. It's like microcontrollers have become, they've taken a lot of the fun out of electronics. So that's 1k, because they're boring. MCU, the little black box, it's all the software and that is doing the work. On the output of the microcontroller, we have two outputs. We've got the one for the LED, and it's going from the positive rail through a resistor, 470 ohm, 471, 47 and 10, 470 ohm, through that little resistor LED to the chip. So we'll just draw that up here. It's going through a resistor and through an LED, a dead LED, to the chip, and that's 470 ohms. And the other output, because there are only two outputs from this chip, goes to a transistor, a NPN transistor, and a 1AM, which is the 3904, probably 2N 3904 really. So that, hold on, I'll just tilt this at an angle. That seems inappropriate, but not to worry, it's what I did. And that goes to the microcontroller. That's an output, and that is a 1K resistor driving that. The 1K resistor is a clue that it's not a MOSFET or something like that, but then again, so is the name of the transistor. Then we have a bit of an oddity. From the positive speaker, the negative connection of the speaker is connected to the transistor, but there's also a resistor connected across that, 390 ohm, for a very specific reason I'll get into in a moment. But there's also a 100 ohm resistor, probably to limit the current spikes. So 100 ohm resistor, 101, 100 ohm, and then it splits and goes through a resistor in parallel with the sounder, the piezoelectric crystal. The resistor value is 391, so that's 390 ohms. That's it. I think I've drawn everything. That is the circuit. That's all we're getting here. Rightio. So to explore this, I'm just going to zoom down a little bit. Standard capacitive dropper with inrush limiter. This basically comprises a 5 volt power supply, but also when you turn the power off, this resistor will make sure it goes right down to zero very quickly, ensuring a nice clean reset of the microcontroller. If you don't do that, sometimes they can crash. This LED, I don't know, does it? It's microcontroller controlled. Does it flash? We could replace that. We could, yeah, we'll do that afterwards. We'll whoop that LED off because it wasn't working the other one either. And we'll put another LED across and see what happens. So the microcontroller is pulsing this transistor, which then pulses this crystal. This limits the inrush because that crystal acts a bit like a capacitor. And that's also why there's a resistor across it, because if it wasn't across it, it would kind of put a charge across that disc, a ceramic disc, and it would initially make a noise, but then that would be it. So it needs a sort of load resistor across it. Either that or you drive it push-pull. But for simplicity here, they've just simply used basically a discharge resistor across that. Not very efficient, but it'll do the job. And that's it. It's not much to it. Right, tell you what. I'm going to get this oscilloscope out. I'm going to scope this and see what it's producing, because I think that is possibly a sort of ramped high frequency waveform. But the only way we're going to find out what frequency it covers is to grab the Keysight and connect it to it. One moment, please. And this is what the Keysight oscilloscope shows us. If you look at the frequency down here, you'll see that it's gradually stepping. You can see it stepping the waveform, but it's stepping up higher and higher to 66 kilohertz, and then it will suddenly reset down, boom, to 24 kilohertz, and it will start the cycle again. And it gradually sweeps the tone over the course of approximately 1 minute and 36 seconds. And every so often you'll see a slight glitch in the waveform, and you can actually audibly hear that from the sounder as a click. Because it's rescaling in the software. Because each of those sections of this square wave actually has a reducing multiple of repeat cycles. And once they get down to a certain level, then they have to decrease the length of each of those cycles and then increase the total number of them again, then start counting down through them again. So you'll see a wee glitch when that happens. However, it's not a nice round binary multiple. It may have been done as an algorithm, but it's possible it was just done as a lookup table. And you can see that glitch and hear the click when it happens. But one of them had about 44 steps and another had 23. So it's kind of almost like manually done just to actually get a fairly linear frequency change over a broad spectrum. And I guess the point of this is they're trying to, say for instance, a cockroach or whatever has a peak of frequency at 33 kilohertz. At some point it will hit that frequency and it will be really annoying, but each particular critter they're aiming at could have a random frequency that it hits, that it is most sensitive to. And by gradually sweeping through all those frequencies, they're hopefully going to find one that annoys the rodent. But there we go, not what I was expecting. That is how it works. It's about to reset again. Click, there it goes. Okay, let's get close. Put an LED in to replace this surface mount one. I don't have one this size. I might have somewhere, but they're very tiny, you know, very hard to find. Most of mine are 1206 size, and this is not. This is much smaller. So let's desolder it by flowing a bit of solder on one end, blowing a bit of solder on the other, and then heating both at once and just sliding it off like that. Put a bit more fresh solder onto the pads. Then I'll get my donor LED, which is most certainly not surface mount. I shall crop the LED leads down and tin them. So I'm just going to grip this carefully so I don't put my fingers on the pins while I'm heating them up. I'm going to put a bit of tinning in that one and on this one. Bit reckless, but not to worry, it's fine. So just double check polarity so I don't get the wrong way around and make a fool of myself. I make a fool of myself quite a lot, that's fine. Now I shall solder that end and this end. Okay, ugly, but I just don't care. Right, what can I use? Now that's cooler. I shall use a long nose plier to just gently bend that LED up without actually snapping it off. Well, actually I'm more concerned about snapping the tracks off. Talking of snapping tracks off, nice enough circuit board, good separation, anti-tracking slots, nice clear design. It's not bad. Absolutely horrific power factor. The Hoppy refuses to even measure the power factor. Talk of the Hoppy, let's bring it up. Plug this into the Hoppy, then plug the Hoppy in. So I shall just dangle it like this so we can see what the LED does. Make sure it's not near anything live. And I shall plug that in, noting that this is live, so I won't go near it. The LED is dimmed up. Oh, and it's dimming out again. Oh, is this one of those Apple-style breathing LEDs? Oh, hold on. Let me turn the light off here. It's getting brighter. And then it's getting dimmer. It's one of those breathing type LEDs effects. Oh, that's quite interesting. Watch your eyes, the light is coming back. That's quite interesting because how did they implement that in software? Oh, I know what it would have been. The steps of the pulse width modulation are probably also along the lines of the frequency output. Not sure about that. Oh, that is quite complex. That is a sneaky piece of software. This is unplugged before I unplug this. That is quite complex. Now, these things are controversial. The manufacturers of them have been hauled over the coals in the past, and some were warned and just kept putting them out with the same claims. In reality, independent tests have shown that they have, at the very best, a temporary effect on repelling rodents, because imagine if you worked in a factory with a lot of noise, or you worked in a nightclub, or in a theme park with the same loop of music going on all the time. After a while, you just get used to it in the background and you ignore it, and it's just your brain just mutes it out, and that's probably what happens to those as well. That's certainly what they thought, the researchers. But when you look at listings for these, you find people glowing, enthusiastic about how wonderful and how they just turned it on and all the rodents disappeared. So I'm not sure about that. Oh, I'm telling you, looking at this, where they've sewed onto the back of this, they've damaged the surface. But it still works. It's actually gone. They've taken some of the metallization off. You have to be really careful with the soldering onto these discs. Pretty much, maybe low melting point solder, but pretty much soldering some on and just basically dabbing the iron on just to get a pull, and then getting the wire on, just dabbing it just to actually just reflow it as quickly as possible without damaging the conductive layer. But there we go. It's very minimalist. It's not going to be loud. Goodness knows if it's going to have an effect, but I suppose ultimately if you plug it in, you'll get a plug that does what they said. It puts out ultrasonic ramping frequencies, and it's got a little LED that just glows up and down, Apple style-y. So yeah, I don't know. Let me know in the Comments down below if you've ever used one of these and if it had any effect, or if you think it's a worthy technology, or if it's a scam. Keep in mind that I'm pretty sure I've opened some of these in the past that had nothing in them other than an LED, that had the disc in the front but not connected to anything. It just seems to be a common scam on eBay.